Hello. Yeah. So today I'm going to talk about the enablement of the secure boot with GRUB under the UEFI firmware on specifically for the x86 based Linux platforms. Since morning we have heard many of the secure boot specific keywords like PK, KEK and many other things, right? So I'm going to deep dive into those. Okay. So myself, Sumeet Pawnikar, I am software architect at Cisco. Mainly, I'm the Linux enthusiast. So I am like Linux device driver and the kernel developer. Also, I work on the low-level firmware side on the core boot development. Also, maintainer for the x86-based thermal and power management subsystem under core boot, and also having few patents. So currently I'm working at Cisco, but my prior experience at Intel and Samsung. Okay, so we are going to cover few of the main topics of the secure boot, specifically from the Linux aspects, right? So here are the few points. UEFI secure boot components we are going to talk about, then few of the types of the keys and what are the databases are there. What are the dependencies in the Linux kernel and how to configure those. Also signing the different binaries, right, which are required to make the secure boot. Also using those different utility tools to sign those binaries and make available. And at the end also I will touch upon how to enable the secure boot on the virtual machines. Okay, so in today's world, why we need a secure boot? I think most of us know that we need to ensure that only trusted and authenticated boot binaries should load. If any malicious programs like root keys, boot keys, or any other malwares gets loaded, then it creates a problem for any kind of a systems, right? And at the end, it is very hard to detect as well. So what we have done at our company, from the small products like from the IoT systems to the client server platforms, we have made the kind of a strict requirement to make like secure boot has to be enabled in each and every phase, like OS requirement, feature requirement, firmware requirement, and at the end, overall, it is the product requirement to have the secure boot enabled. Okay, so as we all know, right, secure boot is kind of the industry standard now, and it is mainly comes under the UEFI. UEFI developed the first time the secure boot because the legacy BIOS didn't had the support of the secure boot. And also there are the kind of many other features where required to have the security when the first instruction gets loaded on the system from the hardware side and comes to the next to the OS level softwares. It is required to create a kind of a chain of a trust. So for that we had enabled the secure boot feature, and with that we create a complete root of trust with the boot chain mechanism where many different boot binaries gets involved in this. How the chain of trust works is like each and every binary modules get verified before it gets loaded with the different cryptographic keys. So at the end of the complete root of trust, with completely all the binaries gets verified and makes the full chain of trust to load. From the first instruction gets loaded on any SoC platform or any IC in that matter, and at the end when the OS comes up. Okay, so we talked about the different cryptographic keys, right, which are required. But what are these different keys and what are the database? So there are the different platform keys, which are like a master or kind of a certificate keys. It is mainly provided by the OS vendors or the device manufacturers and also from the Microsoft side. Another variant is the KEK, key exchange key. So KEK is like the list of the signature list, which is the set of the certificates which EFI can understand and load the EFI binaries. So this is the one of the important key required to load the secure boot binaries. Also, it helps to verify the different signature of the entities and the database. There are the different database are there. Approved list of the certificate database and also blacklisted database maintained. Now, we know UEFI in detail, but I'm just going to reiterate that the UEFI is like more replacement for the legacy BIOS. And what it does is like it does the post power on self test. It checks the boot order, and also it scans the different hard disk images for the partitions and the different bootloader code. Also, it can dynamically load and find the different hardwares and initializes those. So majorly UEFI enforces the secure boot policy on any platform. It checks the signature of the various EFI binaries and makes sure that before it gets loaded, right, it verifies the signature of those binaries. So what EFI does, it first loads the Shim binary and verifies the signature of that. If the signature verification is successful, then only it goes and executes the Shim binary. All these binaries are in terms of the EFI format. That's what it has to be understood. Now, Shim. So Shim is normally first stage bootloader, and it is mostly provided by the Microsoft or other Linux OS distributors with the signed keys. Now, what Shim does, Shim creates the kind of a bridge between the UEFI and second stage bootloader GRUB. What Shim does is it first verifies the signature of the GRUB, and then it successfully verifies the GRUB and it loads the GRUB binary. If GRUB binary is not authenticated or not successfully verified, then Shim can give the error like the bad Shim signature, and then it stops the complete booting process. So normally we see a blue screen with the kind of a security violation, and it stops the booting there itself. Now, Shim also provides the secure boot chain trust, as I mentioned, between the UEFI and the GRUB. So Shim has the different facilities also. It can load directly the various EFI binaries as well. So it called as a chain loading of the different EFI binaries. So with Shim, we can directly load the Linux kernel as well. But we have to ensure that these Linux kernel binaries are again signed with the authenticated keys. So various Linux distros, they do the signing of these Shim binaries and then kernel and file system binaries. So this is the way Shim bridges the gap between the UEFI and GRUB and makes sure that it seamlessly checks the secure boot process and boots the OS. Now, next component in the secure boot process is GRUB, as we discussed, right? So GRUB is the kind of a second stage bootloader which verifies again after the successful loading. It verifies the kernel and verifies the initramfs. So GRUB maintains the various configuration files, and GRUB has the different boot menu options also. So GRUB can load the various kernel versions and also the different root file systems. Now, I had the plan to give a demo to sign all these binaries and then show a step-by-step how Shim, GRUB, and kernel binaries can be loaded. But anyhow, so as GRUB has successfully verified the Linux kernel and the initramfs, after verifying it loads the kernel and pass the control to the kernel. And After that, it starts booting the kernel. Now, as we know, majorly the kernel is the main part of the operating system. Kernel also gets verified and loaded after GRUB. It initializes the main hardwares, peripherals, and also the few of the SoC IPs. What kernel also does as a next step, it loads the file system and mounts the file system as well. And then at the end, it starts the different systemd or the init process. Now here I have mentioned a few of the important kernel files which are dependent on the UEFI. So to make the secure boot enabled in the Linux kernel with the UEFI support, we have to make the few changes in the kernel config files that I will talk in the next slides. But having said that, here are the few list of files which are more UEFI specific, firmware specific files. And what it does that it enables the EFI variables to load the EFI binaries and then mount the EFI variables as the modules. So what it does, it also provides some kind of a support to the Linux boot process for specifically in x86-based architecture, right? A header.s is the main file where the first code starts executing. So there are also the few of the UEFI-based functions are registered. So if system is booting with the UEFI, right? What it does, it registers the EFI subsystem with the firmware subsystem, and also it registers the EFI ware subsystem with the EFI subsystem. So this way it creates the complete chain from the firmware side to the EFI subsystem, and then it hands over to the Linux kernel. So here are the few kernel configs I have captured, which can help to enable the UEFI support in the Linux kernel. So there are two main kernel configs are there, config EFI and config EFI stub. So config EFI is provides the runtime service support for the EFI-based binaries and the variables. And it enables to use the EFI firmware directly on the Linux kernel side. Another config is the EFI stub, which provides the support for the BZ image, normal kernel image, right, to directly gets loaded without the intervention of the GRUB or any other second stage bootloader. So this way, EFI firmware can also directly load the second stage kernel. Now we talk about the complete flow and what are the modules are involved in secure boot. Now let's look into what are the tools required for signing the different binaries. As I mentioned earlier, there are Linux kernel, UEFI-based GRUB, and then initram-fs has to be signed. So normally, more secure OpenSSL utility can be used to sign the different these binaries. So main binaries are like .key and .crt. These are the main private keys, and the certificates are getting created with this OpenSSL utility. And also note that we have to convert these certificates and the key in the ESL format, which is like more EFI can understand this signature list and load those binaries using the SIM OpenSSL engine. Another utility is the mock util. This is the machine owner keys generated using this utility, and it is required to load and understand the specific EFI binaries using our own MOK keys. And one more utility is the SBSign tool, which is used to sign the EFI binaries specifically for the various kernel modules and the root file system. It also provides the kind of facility to attach the digital signature using the private keys and corresponding certificates. Now, there are the different binaries what at the end need to be signed with these tools are the GRUB image and the kernel and init RD image. Normally, the Shim and UEFI binaries are provided by the OS vendors or the device manufacturers. Now here I have captured the complete command how to manually generate our own keys like PK and KEK. The important thing here is the type of the certificate, which is the RSA type algorithm being used with the 2048-bit encryption and also the X509 certificate type. Normally what it does, this command, it creates the various key certificates and also the KEK binary files. Now, what we have these all keys available, we have to add those in the database, right? So third command is to add those files and the keys in the database. After having the all keys and the database available, we have to make sure that it has to get enrolled in the UEFI current existing framework. And then when next time it boots, it takes those latest created certificate and the PK keys. So MOK util is the utility being used to import those DB and the KEK and PK certificates in the UEFI database. When we enroll these keys, right, it asks for the password and need to set those password and remember those, and also can be saved in a file. So when next time it boots, right, it can take that password and boot seamlessly. So here is the command to sign those specific bootloader GRUB binaries and the kernel image files. Normally, the main important thing is using the SB sign utility. We have to provide those DB keys and DB certificate, which we generated earlier, and sign those GRUB binaries and the Linux kernel binaries. Normally, these GRUB binaries are under the boot EFI partition under GRUB, and the kernel binaries are under the boot partition. So once we configure and sign these binaries, right, we have to make sure that to load these EFI signed binaries and the kernel images. So when we reboot any Linux-based systems, we have to go to the boot manager and enable the UEFI secure boot option under that. And if it asks for the password, you remember we have set the password, we need to enter those password or provide that certificate password file to boot it successfully. Now, we talk about the normal secure boot process, but how about on the VM side, right? So I have captured here the few of the utilities which are required as a prerequisite to create the VM with the secure boot enablement. I will not go much detail in that, but there is a command mention how to create the virtual machine using the KVM. Main utility here used is the VRT install to create the VM. The important thing to note here is that in that command, the last argument and with the option -- boot UEFI, which is required to make sure that secure boot is enabled with the UEFI. If we don't give this, what happens that whenever the default virtual machine is getting created, it takes the legacy BIOS as the firmware and then it does not enable the secure boot. So this is the must as an argument to have the secure boot enabled with the UEFI firmware. So once we have this VM created, right, what we need to do, boot the VM and then under the UEFI settings, select the specific signed kernel and the initramfs images and boot those binaries. I have provided the commands to create the VM and then check the status and debug and how to list which are the VMs are available. Now, this is the GUI-based VM creation. The virtual machine manager, VMM, is provided as the UI utility to create the VM. The important thing while we are creating the VM with the UI, there is one option to be selected as the customize the configuration before installation of this VM. It is must because after creating the VM, we'll have to modify the firmware type and then select the firmware type. Instead of BIOS, it has to be the UEFI-based image. So after creating this VM, we can load this VM and successfully secure boot is enabled. Now, this is the last slide. I have observed that in our many of the customer products and the platforms, secure boots are not enabled. So what we had created, like how to cross-verify the secure boot is enabled on the many platforms, specifically on the Linux-based platforms. So my request here to everyone, if they are using the Linux-based any systems, IoT or the server edge, the client platforms, even with the VM, please check that secure boot is enabled or not under UEFI. Okay, so I have provided some references here to look at, and let me know if there are any questions on this.
All right, thank you so much, Sumeet.
Thank you.
Oh, was there one question? Sure, one question.
Yeah, thank you very much. I just want to get into the recording. The mock-util enrollments that you did of the PK and the KEK and the DB, that is actually not necessary. That should be managed at the UEFI setup level.
Okay, sure. Yeah, thank you.